Hello everyone. Welcome to this video on direct and indirect control of pneumatic cylinders. I'm G.Madhumitha, working as Assistant Professor in the Department of Mechatronics Engineering at SRM Institute of Science and Technology, Chennai. Before we go into the details of direct and indirect control of pneumatic cylinders, let us try to understand what a cylinder is. In any physical system, the means through which you get an actuation is by an actuator. In fluid power systems, when pneumatic air is used as a source, it is called as pneumatic systems, and those equipment or element which is used for creating an actuation in a pneumatic system is called as a cylinder. There are different types of actuation that can be accomplished in pneumatic systems, like linear actuation or rotary actuation, but pneumatic systems are more prominently used for creating linear actuations, and those actuators which are used for creating the linear actuator are called as linear cylinders. So an air cylinder or a linear actuator is nothing but an operative device which uses the energy that is stored in compressed air, which is also called as pneumatic power, to convert it into a mechanical actuation or a mechanical and output power. There are different types of cylinders that are in use depending on the application, and the most commonly used are single acting cylinders and double acting cylinders, despite other special cylinders in use based on their applications. To start with, a single acting cylinder will look like this, and it is so called because the actuation of this type of cylinders can be controlled in only one direction, and it consists of only one input port through which the air inlet or outlet can be controlled. The symbolic representation of a single acting cylinder will look like this, where the cylinder, which consists of a piston and a piston rod, is held in place by means of a spring, and depending on where the spring is mounted will decide what is a type of a single acting cylinder. And a double acting cylinder is so called because the actuation of this kind of a double acting cylinder can be controlled in both the direction, and it consists of two ports for fluid inlet and outlet, which can be controlled according to the actuation of the cylinder. And the symbolic representation of a double acting cylinder looks like this. Let us now try to understand the nomenclature of a double acting cylinder, where a double acting cylinder's cross-sectional view is shown here. Inside the cylinder's body, a circular disc called piston will be present, and the area occupied by this piston is called as piston area. On the other side, on one end of the piston, a rod will be attached, which is called as a piston rod, and it is this piston rod's movement will basically create an actuation in the physical world when the cylinder is actuating. And the area that is occupied by this piston rod is called as a piston rod area. The difference in the area between the piston rod and the piston rod area is called as a ring area of the cylinder. The side or the end to which the piston rod is attached is also called as a rod end of the cylinder or the front end of the cylinder, as you can see from here. Whereas the opposite side of it is called as a rear end or the cap end of the cylinder. And accordingly, the port which is connected near the rod of the cylinder is called as a front end connection or the rod end connection, and the port which is connected near the cap end of the cylinder is called as a rear end or the cap end connection. If air is made to flow, or compressed air is made to flow into the cap end port of the cylinder, the compressed air will occupy the piston area, will occupy the cap end volume and try to exert force on the piston. And this makes a piston to move, and the piston rod will come out of the body of the cylinder, and this stroke is called as the forward stroke of a cylinder or extension stroke of a cylinder. Meanwhile, the air that is occupied in the rod end of the cylinder will try to escape through the front end connection. The reverse of this happens in the return stroke or the retraction stroke of a cylinder, where compressed air will be made to pass into the cylinder through the front end connection, where the fluid gets accumulated, the compressed air gets accumulated here, exerts pressure on the ring area of the cylinder, and this will make the cylinder to retract. This is also called as return stroke of the cylinder. Meanwhile, the air that is occupied in the cap end will try to escape from the cap end connection. On either side of the piston, a metallic body that you can see from here, are nothing but the cushioning of a cylinder, which is used to reduce the impact of hard piston strokes when the cylinder is reciprocating. And let us try to understand the cushioning of cylinders and how do they work in a different video later. To consider a single acting cylinder. A single acting cylinder will consist of a spring held against holding the piston rod against the piston in the cylinder's body. It can perform work only in one direction, whereas the return movement of the piston is basically affected by an inbuilt spring, and the external force that you give through the compressed air here will make or will act against this inbuilt spring force, and this will make the piston to get will move, compressing the spring. Meanwhile, there should be some mechanism which will escape the air that is present in the rod end of the cylinder, and that is effected through a small opening that you can find in the rod end of the cylinder. If the air that is supplied to the cylinder at the cap end is removed or stopped, then because or a return path is created for the air to escape, now the spring force will come into action, and this spring, which was so far compressed, will expand. When it tries to expand, it pushes out the air that is present in the cap end out of the cap end port, and thereby this single port of the cylinder will act both as an inlet for the air during the extension stroke and outlet for the air during the retraction stroke. Meanwhile, when the piston is retracting, the small hole that is present in the rod end of the cylinder will also ensure that air is sucked in into the cylinder's body when the cylinder is retracted. So it is basically the spring force that helps in returning the piston to the home position when the compressed air is not given into the cylinder. So as can be understood, for the cylinder to extend, compressed air is to be given into the cap end, and for the cylinder to retract, the spring force will act and it will make the piston to come back to its initial position with a reasonably higher speed. And this means that always the retraction stroke of the cylinder will be faster than the extension stroke of a cylinder. And this is accomplished because of the compressed spring. And the stroke length of this single acting cylinder will be limited by the natural length of the spring. Typically, standard single acting cylinders are available up to 100 millimeter of stroke length. In direct control of a single acting cylinder, the single acting cylinder will be connected to the push button operated spring ridden 3/2 DCV, the symbolic representation of which is shown here. The compressed air as it is connected here will be blocked, which is nothing but the normally closed position of the DCV, which is a unactuated position for the cylinder. When the push button is being pressed, the DCV spool will move, making the connection from port number 1 to port number 2 live, and so air will be flowing from port 1 to port 2 into the cap end of the cylinder, which will make the cylinder to extend. Now, if the push button is released, now because of the spring force of the DCV spool will return back, and that will make the normally closed position of the DCV to be connected. And as a normally closed position of the DCV is connected like this, the air that is present in the cap end of the cylinder will escape from port number 2 to port number 3, and it will be exhausted into the atmosphere. And meanwhile, the spring which was compressed so far when the cylinder was in the extension stroke will now expand freely, causing the return stroke of the cylinder. So as the name suggests, the DCV, which is controlling the single acting cylinder, is directly actuated by means of a push button by a manual operator. And typically, this kind of direct control will require the DCV to be placed very near to the cylinder, and this is most suited for low pressure switching applications. Whereas in indirect control of single acting cylinder, the DCV, same 3/2 DCV, but it is not controlled manually. So it can either be a pilot actuated DCV which requires a pneumatic air supply, or it can be a solenoid actuated DCV which will require an electrical supply for the solenoid to get energized and actuate the DCV is required. So the type of DCV that is required for controlling the cylinder for an indirect control will be a 3/2 pilot actuated spring return DCV for a pneumatic actuation. Whereas for electro-pneumatic actuation, we will require a 3/2 solenoid actuated spring return DCV. And this DCV will act as a main DCV which controls the actuation of the cylinder. Whereas the actuation of this DCV in turn is controlled by another DCV which can be manually actuated from a remote position or from a remote place. And this can be a push button or a foot pedal actuated, or by any means a manually actuated 3/2 DCV. So the pressure in which this 3/2 DCV can actuate, this remote DCV can actuate, can be at a lower pressure, and the DCV which is connected very near to the cylinder can actuate at higher pressure. And so this is typically indirect control is preferred in applications where high pressure switching is required, which can be effected by a low pressure switching with the help of a DCV like this, which can be remotely operated manually. And hence this kind of a control is called as indirect control of a pneumatic cylinder, and in this case it is a single acting cylinder. Now for a double acting cylinder, double acting cylinders will have two outlet ports. Two ports both can act as inlet as well as outlet depending on the actuation of the cylinders. And for controlling this minimally, at least we will require a 4/2 DCV or a 5/2 DCV, which means there should be two outlet ports from the DCV, one connected to the cap end of the cylinder, the other connected to the rod end of the cylinder, and the direction of a fluid flow into and out of this port will be varying depending on the stroke of the cylinder. And as could be observed that the cap end volume of the cylinder will be comparatively larger than the rod end volume of the cylinder. This is because for a double acting cylinder as shown in the figure here, at the rod end of the cylinder, there is a considerable amount of volume that is occupied by the piston rod. And hence the amount of volume that is required to cause retraction of the cylinder will be lesser than the amount of air that is required to cause the extension of the cylinder, and hence the retraction stroke of the cylinder or the return stroke of the cylinder will be comparatively faster than the extension stroke of the cylinder. And this is accounted for these two reasons. One is the cap end volume is larger than the rod end volume of the cylinder, and hence the amount of volume that is, or a volume of a fluid or compressed air that is required to cause retraction of the cylinder will be lesser than the amount of volume required to cause extension of the cylinder, and hence the return stroke of this cylinder will be faster than the forward stroke of the cylinder. And this type of a cylinder or double acting cylinders are also called as differential cylinders because of this difference in speed, a difference in the volume between the cap end and the rod end. Now let us try to understand how do we control the double acting cylinders directly and through indirect means. A direct control of a double acting cylinder will require a manually operated DCV. For a double acting cylinder, we will require a 5x2 push button actuated spring return DCV. So port number 1 will be the source port. Port 4 will be connected to the cap end of the cylinder. Port 2 will be connected to the rod end of the cylinder. Third port and the fifth port will be the exhaust ports, which will be opened up into the atmosphere. When a manual operator presses this push button, the left hand side actuation of this DCV will be coming into contact, and fluid flow will happen from port number 1 to 4, which will make the cylinder to extend. At the same time, volume that is present in the rod end of the cylinder will escape from port 4 to port 5. On the other hand, if the actuation of this push button is stopped because of the spring force, the right hand side of this DCV will be connected, and hence flow will happen from port number 1 through port number 2. It will enter into the rod end volume of the cylinder. As fluid occupies the rod end volume of the cylinder will be retracting. Meanwhile, the air that is present in the cap end will try to escape from port 4 through port 5 to the atmosphere. And this causes the retraction stroke of a cylinder. And this is a direct control where the main DCV, which is controlling the actuation of this cylinder, is controlled manually by means of a push button. Whereas in indirect control of a double acting cylinder, the main DCV which controls the actuation of the cylinder will be controlled by means of a pilot port or a pneumatic port, which in turn will be controlled by a manual operated DCV, which can just give a single pilot line to cause the DCV spool to move. And this can be effected with the help of a simple 3x2 push button actuated spring return DCV. And now when this DCV is pressed, fluid enters into the pilot port of the DCV, making the spool of the DCV to shift to the left side actuation, and which will make the air enter into the cap end of the cylinder, causing the cylinder to extend. And now if the push button is released because of the spring force of this DCV, the normally closed position will be connected, which will cut off this air supply to the pilot port, which will make the spring of this DCV to expand, and the right side actuation of the DCV will be connected, which now allows the air to enter from port number 1 to 2, causing the causing the cylinder to retract. So this is a indirect control of double acting cylinder where the fluid flow into the cylinder is controlled by a pilot actuated 3x2 DCV, pilot actuated 5x2 DCV, which in turn is controlled by a low pressure pilot line coming from a manually actuated DCV, which can be located at a remote place. To summarize, let us try to understand the differences between the direct control and indirect control of pneumatic cylinders. So in direct control, the operator has to manually actuate the DCV, which acts as a primary valve that directly controls the fluid flow in and out of the cylinder. Whereas in indirect control, a low power or low pressure pilot signal, it can be a compressed air pilot line in the case of pneumatic, or it can be an electrical signal in the case of electro-pneumatic system, which shifts the pilot valve and actuate the high capacity, high pressure valve that controls the fluid flow into the cylinder. Typically, in direct control, the entire flow that is required for actuating the cylinder will be happening through the DCV itself. So the kind of a DCV that should support in direct control should support high flow rate through it to pass through. Whereas the main valve can handle high flow rate in the case of an indirect control DCV, and the switching can happen only through a smaller low pressure handling pilot, low pressure handling manual switch or manual valve. And comparatively, direct control is a simple, which is easy to make, requiring only lesser components, whereas indirect control circuits are more complex and requires minimum of two valves, a main control valve and a pilot control valve separately to actuate it. And safety aspect wise, direct control of cylinders is potentially unsafe for operator because they are working with switching high pressure at a higher flow rate of the DCVs, which is controlling the cylinders directly. Whereas in indirect control, it is highly safety, as the operator who is interacting, who is manually controlling the DCV, is only handling with a low pressure or low voltage system, which actually sends the pilot signal to the high flow rate and the high pressure handling DCVs. Distance wise, the installation requirement for direction control valve is limited, and the control panel must be very close to the cylinder to avoid the lag in the response, or to avoid delay in the response of the valves. Whereas in indirect control, they are typically designed to be used in longer distances, and hence it can be set up in unlimited distances required, and the pilot signal can travel along long distances without pressure or signal loss. And the suitability is direct control of cylinders is required for smaller cylinders, low forces, low pressure, simple and standalone systems, which are potentially safe to operate with at lower pressure conditions. Whereas indirect control circuits are suited for larger applications which require heavy duty cylinders, which are operating at high flow rate and high pressure, and in mostly industrial automation systems. And this summarizes the features of direct control and indirect control, and you can decide on, when you are automating your system, you can decide on when to apply direct control of cylinders and when to apply indirect control of cylinders. Thank you. And have a start small and learn consistently, and that will be your success. Thank you.